Back to this computer. Okay, so what we gonna do today? Today we're gonna discuss the task number 4, when we need to unite all the knowledge from the task 1 to 3 and to design a concentrated power system scheme with auto-frequency automation. So we have 3 steps to do this. Let's start with the easiest scenario when we have again only one type of power generation. So the first scheme here we could see when the concentrated generation is from the CHPPs. So here we could see that the number transfer functions number 5, 6, and 11 are represented CHPP unit. Okay, this document is for your use, so during this lecture I feel some information in English for you to be clear what to do. Okay, first of all, let's write the task. Task number 4. Out of frequency automation design for CHPP concentrated CHPP rated power system. Okay, task number 4. Let's make this 4.1 for CHPP. Okay. So we for CHPP, okay. Transfer function number 1. This is the rate power. Okay, to be more clear, maybe I'll open the MATLAB to show you some moments. Okay. I need to connect to remote system. Okay, this could take some time. Connecting. Okay. Yes, we see. Okay. I think we will see this. Okay, so I need to not. Oh, I think we could open this. No, I need this one. I need computer. I need wait a minute. Time to next. Okay, just okay. Let me. There's a Blackstone. Okay. I have access to Blackstone. Let's make approach. What happens in later? Where can I connect Blackstone? Very interesting. And this is simulator. Yes, where I can access. What we have. Very interesting. What's wrong? Okay. Underline. Yeah. Okay, I can't reach your Blackstone for today. Very interesting. No. Okay, I have some problems, technical issues, but whatever. So I need to use a MATLAB from here. Okay. Whatever, we'll find a solution. Okay, so we will. I don't need. Okay. Let's wait for MATLAB. Okay, so third one, let's continue with transfer functions. So this third one, second one, this one is power shortage at a time moment. Power shortage for this is low efficient. Number 5 is a periodic transfer function. Transfer function to represent the valve motor for steam flow. Steam, I think, steam. Where T is time of reaction of a motor inertia. Okay. Shit. Okay, this could okay. The next one is this is the semi-periodic transfer function. To transfer power from steam to turbine. From steam to generator. This will be more correct. Okay, number 7. Number 7, this is a static regulation. average value is from 3 to 7%. Number 8, this is integrational transfer function. Function to represent the system and that's the power system in there. It would be 10 seconds. Some average values. Number 9, this is view window for frequency. Number 10 here is it depends, of course, what. Okay, I need to MATLAB. I need to open this scheme. Okay, yes, show you the difference. But okay, we have this represent number 10 is basic frequency. Basic frequency 50. Why this is made in such way? Because to be easier to change this scheme for a 60 Hertz system. Okay, we need some time to run. Okay. Let's continue with basic knowledge with basic parameters. Okay, what else? What else do we have? Okay, 11. This is saturation. Saturation to limit. To limit the regulation option up and down. Power up and down. Let's write power up and down. So, okay. Why so long? Why so long? Student is ready. I wonder. Okay, busy. Busy. We need to run the scheme to compare these two schemes, because basically we're interesting to develop this one. But this is a basic scheme with basic elements. Okay, this one directed. This is okay. Just while waiting, just clearing. Okay. Oh yes, almost done. So this could be the 4.2 rated hydropower plant. Okay, very good. Okay, it is. Okay, so let's get. I've lost some pictures because I need. What do I need? I need to change. I need to change the path. I need to change the path. Maybe it will be any documents. Not need Windows. Okay. So okay, let's try to make this path and refresh. Okay. Okay, yes. I want to refresh. Okay, maybe we could run simulation, then it will find. Okay. Okay, some problems with pictures, unfortunately. Okay, okay, no, okay, it's found. Yeah, so if we want to run this scheme, yeah, with all the pictures from your MATLAB, yeah, you need to change the path here in MATLAB, yeah, to the map where you have the program, no, the scheme and all the pictures. That was, I opened just a scheme, yes, without changing the path. That's why for the beginning, without the pictures, yes, to show the transfer functions. Okay, so let's see in this example what I have for the task number 4 and what we see from the task number 1. What is the difference? First of all, I want to highlight that this is first for hydropower plant. So this is the second 4.2. Yes, 4.1 is for CHPPs. That's why we change here with these elements number 5 and 6. And here is the element, these two elements. Yes, we change these two elements because, yes, we have different type of a generator. The next one, the new element is number 11. Here we don't have this element, yes. And this is one, okay, I'll say for you, this is one of conclusions, yes, because we run here, we have a deficit. Oh, please open. Please open. Oh, it's paused. I need to continue. It's not done. Okay, already terminated. Okay, so it's done. Okay, simulation is done. What you see here is we see the power drop, frequency drop, and then frequency restoration. And this restoration means that we decreasing the imbalance. But as I say, the regulation possibility is from T to 7%. It's not big. You know, for example, for here, yes, it is written here 0.2. It means 20% shortage, yes, of power. And the regulator could add about 5%. Okay, we could check what is, yes, regulator could push 5% of power more, but shortage is 20%. It means that regulator can't stop the frequency drop. If we compare two values, so we have possibility with regulator produce power more only for 5%, but the shortage is 20%. So the difference is 50%. This difference of 50% means that the frequency will continue to drop because the system is in a balance. But what do we see here in this? We see that this regulator, yes, starts, no, okay, regulator pushes more power. We see this, that the frequency started to restore, but what we see next, it stopped to fall. Why? Because this scheme is simplified and there is a leak of one very important element or answer function for this scheme. This element is 11, saturation. This saturation in this scheme means the limit of a regulator impact, because okay, yes, it is true, the regulator possibility option is only 5%, but the regulator add 5%, add 5% more, add 5% more, and so on. So this is how to say the negative the negative side of this simplified scheme. So to make this scheme more correct, we need to add one more element, the saturation, and to make their limit of 5%. So yes, this regulator defines how much. Yes, But we need, how to say that 5%, yes, it is not only a step for regulation, but it is also a limit for your regulation option. That's why, to be more clear, to be more correct, we need to put to this scheme this one more element, more trans function with a name saturation to limit this option. Okay, what else? So what else different? This element is this coefficient number 4. This element is 2 and 3. What is the difference? Here is only one delta. Sorry. I'm wrong. 3, number 3, as it is written in the description, is the same as P. But this 0, it is hidden. It is hidden. Let's see. It is hidden here. So it's just hidden here. So yes, when we push here, yes, we see that this is saturation, and these two elements just are united together to this block. Yes, so okay, because this one elements number 2 and element number 1 is the initial state. What is initial power and what is initial shortage? So if we put 0, 0, it means that system is in balance at initial step of modeling. And what is else here? Yes, we see that we have separated here, we got only one, but here we separated this one into 2 parts. So this one is number 8 and this one is number 10. This is this bus and this is number 15. So this model, yes, this block in this scheme is just separated into 2 elements, 8 and 10, yes. But typically all other things are the same. So this is how to construct this scheme and what is the difference, yes, of this scheme and the basic scheme from the task number 1. Okay, this is a basic difference, how to build this scheme. The step number 2. Okay, maybe a little bit different sequence. So this is how to build a CHPP concentrated power and the 4.2 concentrated HPP. So for this purpose, you see, we could use these scheme elements. Don't worry. Here maybe there is a little bit different because you see all these elements are the same here, and only this one is a little bit different, but it doesn't matter because it depends on what type of unit we are modeling. So you could use as it is in the first task. The only one different, we need to put a saturation, yes, like it is here, yes, to limit the regulation possibilities. Okay, so I think I need just to retranslate some elements. Okay. Whatever. Okay, I think I need to write so. You can use HPP scheme from task 1 instead of elements 1, 4, 2, 3, and 4. Okay. Because all other elements are the same as here for scheme, for CHPP concentrated scheme, yeah? So the difference is we have different type of generator. That's why we need to represent using different transfer functions. Okay. Next one, 4, 3. Auto frequency automation design. Okay, what is the idea of this design? Block number 5. So what is the under frequency automation? Once more, as it was told in previous lectures, we have frequency set points, and if frequency drops below the set point, we disconnect some type of load. So we have designed out of frequency automation to disconnect the load we have chosen if the frequency drop to the set point 1, different type of load. Of course, when we make the analyze, what type of load could be disconnected first, what type second, what type third, and so on, because we have different groups of load, very important, for example, to hospitals, schools, and so on, and less important load. So that's why making this decision, yes, we need to analyze who will be first, who will be second, and so on. For example, for industry where the cost of unplanned interruption, yes, of electricity supply costs a huge amount of money. Yes, of course, we try not to disconnect them first, yes, because we have a lot of losses, yes, due to this kind of operation. Okay, so in this way, how we design this automation? Very simple. So each step, each stage is represented by the block number 1, 2, 3, 4, and 5. So it depends how many steps for auto-frequency automation we are going to design. This means in parallel how many steps will appear in this block. So what do we see here? First of all, the element number 1, as you can see here, it's a switch. Yeah, the 1 is a signal, it is input block. Yeah, for this block it's input. And here we could see the switch. No, the switch ID is a trigger. Yeah, so if signal appears, it goes next to the block number 2, which one is a saturation. So, okay, 1 is a switch. Second is saturation. With 2 set points. On, off. Why do we need to put these 2 set points? This is very simple because no, in a real life, every stage could be used only once. It means that we could disconnect the load number 1 only once. But for this modeling, you see, during the scenario, you could have this fluctuation of frequency. You have disconnected the load, the restoration of frequency began, and the second shortage, for example, appears. Yeah, so the frequency goes down again. That means to stop the possibility to use this stage the second time, we need these blocks number 1 and number 2. That's why we need these 2 set points. Yes. The block number 3, it's just a transfer function like time delay. Because like it is in real life, we need time for, how to say, we have a signal, we have a command, but we need time to implement this command. That's why, to be this scheme more realistic, we use this time delay. Number 4, it's logical end. And number 5, it's a giant function or how much load are we going to disconnect for this stage? So 0.07 means 7% of load, yes, is connected to the first stage, and it means that the frequency drops below the 49 49.6. Okay, we have two saturations, up and down, because this is inversion, to be clear. This is just an example. This doesn't mean that you need to use the same values, but just, okay, so if this saturation goes down, yes, 1949.4, this is a step. We'll disconnect the 7% of the load, and the same. Here you could see the different, yes, different values, yes, of a set point, and so on. Okay. And here is just an example. This is stage out of frequency automation. Stage number load percent, and this frequency set point. Okay, so this how this block could be designed, yes. And this is 4.4 mixed concentrate. Mixed concentrated mixed concentrated power generation. So here we could see here two types of CHPP, okay, CHPP and HPP. To make this mixed system, we understand that in our power system we have mainly two types of, for example, like this for Latvia, two types of power generation. We have hydropower and we have a thermal power. And for this, yes, we need to, okay, saturation. Okay, maybe one very important for saturation. Where it is saturation? We have saturation 11. Saturation, yes. So for 5% set point is, no, it means that 5% more, so or less. So 5%, this is high, 5% more, set point high. Okay, up and down. Let it be up and down. Okay, so saturation, yes. So for here, yes, it means we could, for saturation, yeah. This saturation 6, the block name, and plus saturation 7. in total 1.05 approximately. Why? What is the idea? Because, for example, we have 30% of hydro and 70% of CHPP. Each one has its regulation and possibility to produce more. So 5% from 40% for hydro, and for example, 5% from 70% for CHP. So in total, it means that the total saturation will be about 105%, yes? But it depends how we divide this power to every source of power. So this is very important, yes. And that's number 4. Okay, so what to do? What to do? Design. Scheme 4.1, 4.2. Design automation 4.3. Design scheme 4.4. For automation 4.3. Choose number of stages and set points and load power in percent. Simulate different scenarios for every scheme. So 4.1, 4.2, 4.4 to analyze your, what can I say, design. Is it good enough for simulation scenarios? Choose power shortage. Power shortage, block number 3. Block number 3 from 0.1 scheme from range 10% to 50%. Design isn't good enough for simulation scenarios. Choose power shortage for, okay, for a report. Make print screen of reference for every scenario plus great plus scenario description. Okay, and plus this is what. Okay, so this is all for the task number 4. So you need to make 3 schemes, you need to design automation, you need to develop different scenarios. It means that with different set points. Okay, maybe I need to highlight this more. So to find a good design of automation, you will need different sets of set points. This is correct points, set points, and load power. Okay. So maybe once more. Design schemes. No, develop schemes, design automation with different set points for frequency, different set points for load power disconnection, run scenarios, analyze scenarios to find the best automation design with analyze, of course. So this is the task number 4. And this is all what you need, yes, to finish this subject. So first 3 tasks, how to say, just to understand what is going on. Second, for your personal design. Basically, 3 first tasks, they must be finished, and based on the results of the task number 4, I will put you a mark. So how good is number 4? So good mark will you have. Okay, this is all for the task. So you have lots of about 10 weeks. Yes, you could come here to this computer class. You could use your MATLAB. You could make models. You could analyze. You could ask for help if you need to design, and so on. Okay, I'll send this document via email and put this in Ortus as well. So we could stop the share. Okay, we could switch share. This new teams. Go to share screen option. Okay. I want to stop the sharing. I have... Okay, it has stopped. I need to stop record.